Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 19, we confront the final arbiter in rule selection, the minimal grammar principle, the smallest constraint set that still holds. This is the firewall mechanism that resolves the inevitable ambiguity when multiple candidate rules explain the same data. The skill you will gain is that of a principled packer, the ability to audit and compare competing grammars, selecting not the one that is most elaborate, but the one that imposes the fewest, most essential constraints on phi, while still accounting for the evidence. Our core question is, when many grammars can explain the same sentences, how do we choose responsibly? This question targets the problem of underdetermination. Given any finite set of phi sentences, there are always infinitely many possible rules that could fit them. The inference process we built narrows this to a candidate set from a registered model class. But often, multiple, structurally different rules within or across classes will fit the data equally well within uncertainties. How do we choose between a simple rule and a complex one? Between a rule with 3 parameters and one with 30? The firewall's minimal grammar principle provides the disciplined answer. Prefer the smallest grammar that explains the data. This is not an aesthetic preference for simplicity. It is an epistemic imperative. Unnecessary constraints are usually overfit stories. They fit the noise of the current data rather than the signal of phi's true constraints. And they will fail when confronted with new data. The core revelation is minimality is a measure of robustness, not just elegance. A minimal grammar has less room to hide errors, less capacity to absorb noise as signal, and therefore makes sharper, more vulnerable predictions. It is the most auditable, most falsifiable candidate. It is the rule that does the most work with the least assumed structure. In the language of our triunity, a minimal grammar is one that imposes the smallest, tightest set of joint constraints on omega, k, and v necessary to capture the observed relationships. Let's build this principle from the ground up. We have an ensemble of phi sentences. We have 2 candidate rules, GA and GB, from potentially different model classes, MA and MB. Both rules pass the invariance test from part 18. Their predicted quantities Q fit the data with a chi-squared per degree of freedom close to 1. Rule GA is minimal. It might be expressed as the second derivative of position with respect to time is proportional to a central force. In symbolic form for a planet's orbit, this is Newton's law. d squared r by dt squared is equal to minus gm over r squared in the radial direction. Spoken. d2r dt2 equals minus gm over r squared. It has one coupling constant, big G. Rule GB is rich or complex. It might add epicycles, or a distance-dependent gravitational constant, or a fifth force. Its equation might be d squared r by dt squared equal to minus gm over r squared minus alpha over r3 plus beta v squared over c squared r. Spoken. d2r dt2 equals minus gm over r squared minus alpha over r cubed plus beta times v squared over c squared r. It has three extra parameters: alpha, beta, and a reference speed c. Both rules could be tuned to fit the observed planetary orbits, the phi sentences, with high precision. How do we choose? We define grammar size formally. For rule G, its size or complexity is not the length of its equation in characters. It is a measure of its constraint richness. We can quantify this in several audibly explainable ways. Parameter count P, the number of free adjustable parameters in the rule. In GA above, P might be 1, G. In GB, P might be 4, G, alpha, beta, C. More parameters mean a larger search space for the rule to fit data, as we learned in part 17. Functional complexity. This measures the intricacy of the constraint itself. A rule that says force is proportional to 1 over r squared is less complex than one that says force is a sum of 1 over r squared, 1 over r cubed, and velocity squared terms. We can measure this by the order of the highest derivative used, or by the number of independent mathematical operations linking phi derivatives. 3. Triunity, interdependence, complexity. How tightly coupled are the constraints on omega, k, and v? A minimal grammar couples them through the fewest, most direct relationships. A complex grammar might have separate, intricate constraints for each echo that only combine in Baroque ways. The minimal grammar principle states, given two rules GA and GB that fit a data ensemble equally well within uncertainties, prefer the rule with smaller grammar size. But equally well is key. We must formalize fit. We use the Bayesian evidence or the corrected goodness of fit. From part 18, we have chi-squared. A simple fit statistic like chi-squared always improves, gets smaller, as you add parameters. So you cannot just compare raw chi-squared. We need a metric that penalizes complexity. One such audio equation is the Bayesian information criterion, BIC. BIC is called chi-squared plus p times ln n the n. Spoken. BIC equals chi-squared plus the number of parameters p times the natural logarithm of n, where n is the number of independent phi sentences. The rule with the lower BIC score is preferred. Why? The term p times logarithm of n is the complexity penalty. It says, your rule gets penalized for every extra parameter you use, and the penalty grows with the amount of data you have. A complex rule, large P, must achieve a much better fit, much lower chi-squared, to overcome this penalty and win. If two rules have similar chi-squared, the one with smaller p wins. This is the mathematical heartbeat of the minimal grammar principle. Now, why is this necessary? The failure mode it prevents is overfitting disguised as explanatory depth. A rich grammar with many parameters or complicated functional forms can be bent to fit not just the underlying signal in the data, but also the random noise, the systematic errors, and the idiosyncrasies of the specific experimental setup. It absorbs everything. The result is a rule that fits the past data perfectly, but fails to predict new data. It is a just-so story for the existing sentences, not a general constraint. The minimal grammar principle forces us to strip away ornamental complexity, leaving only the structural bones that the data robustly supports. Integrate this with the triunity. This is where minimality gets its true disciplinary power. Minimality must be triunity minimality. we cannot allow a rule to claim simplicity by hiding complexity in just one echo. For example, a rule might propose a very simple spatial constraint, k, space is flat, but an incredibly complex, time-dependent dynamic, omega, a field that evolves with a 20-term differential equation. This is not triunity minimal. The complexity hasn't vanished, it's just been shoved into the omega clause. True minimality requires that the joint constraint on omega, k, and v be as simple as possible when considered together. No hiding complexity in omega while claiming simplicity in k and v. No burying complexity in k while claiming simplicity in omega and v. No smuggling complexity into v via ad hoc, complicated coupling functions between omega and k. A minimal triunity grammar expresses the relationship between the three echoes in the most symmetric, direct, and economical way possible. Einstein's field equations, g mu nu equals 8 pi g t mu nu, spoken as the Einstein tensor equals 8 pi g times the stress energy tensor, are celebrated in part because of their profound minimality. A single tensorial equation linking spacetime geometry, a fusion of k and omega constraints, to matter energy, the source of V-type dynamics. It packs an immense amount of physics into a remarkably compact constraint set. Now connect this to energy as tally. This connection is devastating for overfit, non-minimal grammars. Overrich grammars can explain anything by adjusting the ledger rules. The tally loses meaning. If your grammar is too flexible, you can always make the energy books balance by inventing new forms of energy or new conversion rules. Dark energy, dark matter, quintessence, these are not necessarily wrong, but they are potential complexity injections. The minimal grammar principle asks, is this new term the smallest possible addition to the grammar that explains the data? Or could the data be explained by a subtler, minimal reinterpretation of the existing ledger? If a complex grammar is adopted too readily, the energy tally becomes a flexible accounting tool that can be made to balance under any circumstances, rendering it vacuous as a test of the theory. The operational interpretation is model selection in statistics and machine learning. Techniques like BIC, AIC, Akaike Information Criterion, and cross-validation are all instantiations of the minimal grammar principle. They formalize the trade-off between fit and complexity, preventing the selection of an over-parameterized model that memorizes the training data but fails on new data. The firewall role is that of the pecking gate. You are the pecker for a long, uncertain journey into new data. Your intellectual backpack has limited capacity for complexity. Every extra rule, parameter, or functional form costs you in robustness, auditability, and interpretability. When presented with multiple candidate rules, you must pack only the most essential constraints. You ask, does this extra term in the equation improve the fit enough to justify its weight? Or can I achieve the same predictive power with a lighter, simpler load? You are performing a cost-benefit analysis on explanatory complexity. Let's state clearly what is allowed and forbidden. You may propose a more complex grammar if it provides a significantly and robustly better fit to the data, as measured by a rigorous metric like BIC, where the chi-squared improvement drastically outweighs the complexity penalty. You may also propose complexity if it is theoretically mandated by a higher-order minimal principle, for example, gauge symmetry demanding a new field. You may not choose a more complex grammar over a minimal one when their fit is statistically indistinguishable. Justify added complexity with vague appeals to completeness or realism without quantitative evidence. Ignore complexity penalties when comparing models. Claim a grammar is minimal while hiding complexity in one aspect of the triunity. What happens when the check fails? The license consequence is a directive. The minimal candidate is retained. The more complex candidate is rejected or archived as a less parsimonious alternative. The complex rule may receive a narrow, provisional license only if it makes a unique, testable prediction that the minimal rule does not, and that prediction is the basis for its proposed complexity. Otherwise, Occam's razor, formalized through BIC or similar, cuts it away. Now, we must state the explicit prediction and falsification for the minimal grammar principle. Prediction. A truly minimal grammar will generalize better. It will keep working when you move to new regimes, new omega KV ranges, with fewer patches or adjustments. Its predictions will remain stable as more diverse phi sentences are added to the ensemble. This is the prediction of robust extrapolation, falsification condition for the minimal candidate. If a richer grammar consistently and significantly outperforms the minimal one on out-of-distribution data, data from new omega KV regimes not used in the initial inference, and this outperformance is not due to the richer grammar merely being a patchwork of fixes for the minimal one's failures, then minimality must be revised. The falsification is sustained, superior predictive performance of a more complex grammar in new territories. This is how science progresses. A minimal rule, Newtonian gravity, works until a regime, Mercury's orbit, strong fields, is explored where a richer grammar, general relativity, is unavoidably better. A historical example is the shift from the Ptolemaic epicycles to Kepler's ellipses. The Ptolemaic model of planetary motion was incredibly rich, a grammar of difference and epicycles with many adjustable parameters. It could fit the observed planetary positions, the phi sentences of the time, very well. Kepler's model was radically minimal. Orbits are ellipses with the sun at one focus. It fit the data better with far fewer parameters. The complex Ptolemaic grammar was overfitting the noise of ancient measurements. Kepler's minimal grammar captured the true signal and generalized perfectly to new data, like the moons of Jupiter. The minimal grammar won because it was not just simpler, but more correct. Now let's explore an analogy that makes the stakes of minimality vivid and practical. The crafting of a travel route and supply list for a caravan crossing the Hindu Kush. A master caravan leader must plan a route from Kabul to Mazar-i-Sharif. They have historical travel logs from previous journeys. They must infer the rule or optimal path. Grammar GA. Take the main well-trodden route through the Salam Pass. Pack 1 sack of flour, 1 of rice, dates for energy, salt, and essential medicines. Expect a 7-day journey in fair weather. This grammar has few parameters. 1 route, basic supplies. It is robust because it relies on known, reliable infrastructure and essential, versatile supplies. Take a dynamic path that switches between 3 alternate routes based on daily bird omens and minor road reports. Pack the basic supplies, plus specialty spices, extra tents for every possible weather, gifts for 5 different tribal profiles you might encounter, and a separate set of tools for repairing each type of wagon axle. This grammar has many parameters, multiple routes, conditional switches, excessive specialized supplies. It can account for more specific events in the historical logs. For example, on day 3 in 1922, a rare snowstorm occurred and the caravan had cumin, which helped trade. Both grammars are consistent with the historical travel logs. The complex grammar might even fit the logs more closely by accounting for odd, one-off events. The caravan council, the firewall, must choose. They apply the minimal grammar principle. Does GB fit the historical data significantly better? The odd events, snowstorm, cumin trade, are rare outliers. GA captures the consistent, invariant pattern of successful journeys. Complexity penalty. GB's complexity, multiple routes, conditional rules, excessive supplies, carries huge costs. It's harder to communicate, more prone to error in execution, heavier to carry, and diverts attention from core logistics. Generalization prediction. GA is predicted to be more robust for the next journey. Its simplicity makes it adaptable. If a new obstacle arises, the simple caravan can respond flexibly. The complex caravan is brittle. If the bird omens are wrong or a specific gift is missing, its elaborate plan can collapse. The minimal grammar packs for the known invariants of mountain travel, not the noise of historical anecdotes. The council chooses grammar G_A. The complex grammar is rejected as overfit to the specific details of past journeys, lacking robustness for the future. This minimalist decision maximizes the caravan's chance of a safe, successful passage. The unnecessary constraints, specific omens, excessive gifts, are discarded. In Holophase science, the caravan journey is our exploration of reality's parameter space. The historical logs are our existing phi sentences. The minimal grammar is the rule with the fewest forces, fields, and parameters that captures the robust invariant patterns in the data. The complex grammar is the theory that adds new particles, extra dimensions, or intricate dynamics to fit every little anomaly in past experiments. The firewall's packing gate forces us to choose the minimal, robust path forward, lest our scientific caravan become bogged down by the weight of overfit speculation. Now we state the mandatory episode 11 axioms, now enforced by Minimality. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. Minimality is the engine of effective falsification and scope discipline. A minimal rule is easier to falsify. It has fewer places to hide. It also has clearer scope boundaries. Its simplicity often defines where it should break. A complex rule can be endlessly patched to avoid falsification, and its scope can be blurred by its many parameters. And when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. Under the minimal grammar principle, the first response to failure is not to add complexity, but to see if the failure lies within the rule's license scope. If it does, the minimal rule is downgraded. Only if the failure is systematic and external to a well-defined scope do we consider a richer grammar. And even then, we seek the minimal enrichment necessary. The skill you gain from this part is disciplined model selection. You learn to resist the allure of complex, powerful explanations. You reach for metrics like BIC. You ask, what is the simplest story that fits the facts? Does this new complication pay its way with significantly better predictive power? This skill protects you from building intellectual castles on sand. Elaborate theories that crumble under the weight of their own unnecessary assumptions. This has immediate, critical application in fundamental physics. The search for theories beyond the standard model. Is a new particle or force the minimal explanation for an anomaly? Or could it be a systematic error or a subtle effect within the existing, simpler framework? The constant battle against overfitting. A neural network with millions of parameters can fit the training data perfectly, but fail on new data. Techniques like dropout and weight decay are methods to enforce a kind of minimality. Economics and policy. Is a complex regulatory model with hundreds of variables better than a simple, transparent tax rule? The minimal grammar principle would demand evidence that the complex model's predictions are robustly superior, not just that it fits past economic data more closely. Consciousness studies. Is a simple integration of neural phi patterns sufficient, or do we need to invoke entirely new ontological categories? Minimality demands we exhaust the simpler option first. Finally, Let's summarize the epistemic function of this part. We have defined the minimal grammar principle as the firewall mechanism that selects from among equally fitting candidate rules the one with the smallest constraint set. Minimality is quantified through complexity penalized metrics like the Bayesian information criterion. It requires triunity minimality, preventing the hiding of complexity in any one echo. The firewall acts as a packing gate, forcing a cost-benefit analysis on explanatory complexity. The explicit prediction is robust extrapolation. A minimal grammar will generalize better to new data regimes. The explicit falsification condition is the sustained superior performance of a richer grammar in new domains, forcing a revision of what is considered minimal. The license consequence is the rejection of non-minimal grammars when fit is equivalent, and the downgrading of a minimal candidate if it is consistently outperformed. This strengthens the firewall by providing the final, decisive criterion for rule selection. It ensures that the rules which ultimately earn a broad license are not just well-formed, proof-carrying, type-checked, honestly searched, and inferred from an ensemble, but are also the most parsimonious, the strongest, most distilled essence of the constraint that the data can justify. This is how we extract signal from noise and law from coincidence. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Carry the discipline of the principled packer. In a world overflowing with possible explanations, have the courage and rigor to choose the simplest one that works. This is the final, sharpest tool in the scientist's kit for uncovering reality's true grammar. Now we bridge to our final meta question. Minimality is not a vibe. We must measure what a rule really costs. This leads us to the ultimate valuation engine of the epistemic firewall. Salam, and peace be upon you.